Hi, I'm going to do a real short video on conservation of charge. So when we have charged objects and they're conductors, when we touch them together, they share that charge over each other, and that charge wants to distribute itself evenly. So we have this type of sea level problem where you touch objects together, you need to figure out what the end state is. So here's an example. I have an object with +4 charge, an object with -9, and an object with +12. I'm going to touch A and C together, separate them, and then I'm going to touch A and B together and separate them. And I want to know what is left, what kind of charge is left on each of them. So the process here that I want to take, I'm going to say, okay, we're going to touch A and C together. That means we have a +4 and a +12. All right, they're conductors, so the charges are free to move across and between the two spheres. So this +4, those +4 are trying to get away from each other because like repels like. The +12, same thing. Now if they're evenly sized, which I really didn't do a good job of, if they're the same size sphere, then the way that we're going to get that charge spread out is evenly across the surface of both of those spheres, because every single positive charge wants to get as far away from all the others, which means that we end up with a nice even distribution across all of them. So how much charge total do we have to spread out? Well, we have +4 +12, so there's a total of 16, +16, that's going to spread out on each, which means we're going to end up with +8 on each of the spheres. So we touch them together. The positive charges spread out evenly, we take them apart, and now we're at +8 for A, we haven't touched B, so it's still at -9, and +8 for C. All right, so that's the status now. We touch A and B together, A and B. All right, +8 and a -9. All right, we can use the same idea, say how much is the total charge, and then divide that evenly across the two. So a +8 and a -9 gives me a -1 total, which would give me a -1/2 on each. And don't worry about the 1/2. I'm hiding the little Coulomb sign here, so you can have a half a Coulomb. So that would give me -1/2 here and -1/2 here. The other way that you can solve this is by saying, well, what is the +8 going to do? What is the -9 going to do? So these +8, once they have two charges, two spheres to sit on, are going to go all the way and spread out. So 4 would end up on this sphere, and 4 would end up on this sphere. Likewise, what is the -9 going to do? Well, it wants to split up evenly across the two spheres, so we'd have -4.5 on this one and -4.5 on this one. All right, so then we separate the two spheres. What's left? 4 minus 4.5, -1/2. So in this case, what is left is, okay, I gotta keep track. This was A, this was B, this was C. That's A and B. So A is going to end up with -1/2 on A. B is going to end up with, really? No, oh, there we go. Messed it up myself. And then C is the +8. All right, so that's what I think we're going to end with. And we can check our answer a little bit by saying, all right, charges can't be created or destroyed. If we started with a certain amount of charge across all three, we'd better end up with that same amount of charge across all three, because we can't lose electrons. We can't gain a proton. So how much charge did we start with? +4, +12, -9, so that's 16 minus 9. Our total charge that we had to start. So the total charge to start is, what did we have? What did I just say? 16 minus 9. So we started with +7. How much do we end with? -1/2, -1/2, +8, so 8 minus 1/2 minus 1/2, +7 to end. So we're consistent there. We didn't do a math error, is what this is telling us. So that's the real basics of how to do these kind of conservation of charge problems. Now the order is important. If we reversed the order of this and we touch A and B together first and then touch A and C second, we're going to get a different answer. So let's try that one. We're going to touch A and B together first. All right, so we're starting back here again. And I'm going to touch A and B. So a +4 is going to be contacted to a -9. All right, so the total amount of charge here, 4 minus 9, we have -5 total. So that's going to leave me with 2.5 negatives on each. Okay, so at this step, A has -2.5, B has -2.5, and C still has 12. We haven't touched that one. Now we're going to touch A and C together, so this one and this one. -2.5 is touched to the +12. Ah, boy, I could have picked better numbers, huh? +12 minus 2.5 is +9.5. That's going to separate evenly onto the two surfaces, so 475. Plus 4.75 plus 4.75. So my final condition, if I reverse the order, I got to keep track of these letters. That's A. Okay, so A has -2.5. B, what did we end up with B? So there was A and that was B. So this is A and B and C. So B is -2.5. Oops, that's what I did wrong. I jumped a step. So A, there we go, plus 4.75. B is -2.5. And C is 4.75. And now, again, it should add up to a +7. So 4.75 minus 2.5, so it's 2.25. So 2.25 plus 4.75, that's 1, 2, 3, 4, 5, 6, 7. We did our math right. So the order does make a difference. So you're going to get a different answer if you touch these two together first or if you touch these two together first. So just keep that in mind when you're doing these problems. But that's just the basics of conservation of charge. Real quick version.